let's do the same thing for acetic acid. What are the chemical properties of acetic acid? So first you do metathesis. So hydrogen ions we'll talk about in the acid base, it's easier to talk about. But what about acetate? What are the metathesis properties of acetate? Acetates are going to react with what? Cations. Well, acetates, nitrates, and chlorates are all soluble, so pretty much no reaction. So acetate's not going to show any kind of metathesis. And we move on to acid base. Acetic acid is a weak acid. The weak acids don't completely ionize, so we should keep it together like this. If we look at acetic acid, weak acid, what does it react with? So we're going to use the acid-base chart. Here's acetic acid here. What bases does acetic acid react with? If acetic acid reacts with acetate, then what do we form? Acetic acid reacts with acetate, then we're going to form acetic acid and acetate. And so pretty much nothing forms. And so that means we need a base that's stronger than acetate or weaker than acetate. Like weaker? Like fluoride. Fluoride's weaker. So will acetic acid react with fluoride? If acetic acid reacts with fluoride, what forms? Hydrofluoric acid. So acetic acid donates a hydrogen, forms acetate, and fluoride goes to HF. And so going from acetic acid to HF, is that favorable or unfavorable? It's unfavorable. We're going from weaker to stronger. Same with nitrite. Acetic acid won't react with nitrite. It's too weak of a base. We need bases that are stronger than acetate. So acetic acid will react with bicarbonate. Acetic acid reacts with bicarbonate to form CO2 in water or carbonic acid. Acetic acid will react with hydrogen sulfide. Reacts with hydrogen sulfide to form H2S. These are weaker acids. Acetic acid reacts with monohydrogen phosphate to form dihydrogen phosphate. Acetic acid reacts with ammonia, we form ammonium. Cyanide, we form HCN. Hydrogen cyanide. And so what we can say is acetic acid will react with all bases stronger than acetate. All bases stronger than acetate. Since this stays together, we could treat acetate. Acetate's also a base. We treat it as a base. But acetic acid kind of stays together. Weak electrolytes don't really break apart to a large extent. Just leave it there. Then we go on to redox. Can you burn acetic acid? Will acetic acid burn? We can think of it, when we say burn, we think of it in two ways. One way is you burn it to make a fire. Another way is you burn it as a fuel to make calories. Burn some calories. Both of them accomplish the same thing, because if you burn it in the fire, you produce CO2 and energy. If you burn it as a fuel for calories, you exhale CO2. You get energy from So does acetic acid burn? What would you think? Can you burn acetic acid?
Yes.
Yeah, the answer is yeah, you can burn acetic acid. Acetic acid burns. Excuse me. That means acetic acid's a fuel. Fuel's a reducing agent, so is it? Well, hydrogen is +1, oxygen's -2, and carbon would be what? No, maybe it's easiest if we run it out. This whole thing has to add up to 0 because it has a net neutral charge. So carbon, we have 2 carbon. Carbon must be 0, yeah. This is -2, -4, +4, -4 +4 is 0. So these both have to be 0 for this whole thing to add up. Well, if carbon's 0, well, where does that place it? Well, what's the charge range on carbon? Carbon's charge or oxidation state ranges from what? -4. It's right in the center. And so actually acetic acid can be an oxidizer or it could be a reducer. It could either lose electrons, it could lose up to 4 electrons and be a reducer, or it can gain electrons, be an oxidizer. Well, typically for us, because we live in an oxygen type environment, it's a reducer. Its role will be regulated. And so acetic acid, you can get some calories from acetic acid. If you eat vinegar, you can actually get some energy from eating vinegar. It's not like say, if you sprinkle vinegar on your salad, you're going to get calories, but what if you sprinkle, let's say, limestone on your salad? If you sprinkle limestone on your salad, will you get calories from that? Can you burn limestone? In a way, you could burn it. I mean, you could decompose it into other things, but it doesn't really burn in the redox sense because oxygen's -2, calcium's +2. That means carbon is what? Yeah, carbon is +4. Well, that's maxed out. Calcium carbonate can only be an oxidizer. It cannot be a reducer because it's got no electrons to lose. The only thing that can happen is it can take electrons. Calcium carbonate's not a great oxidizer, just based on experience. There are better oxidizers out there. But if it's going to behave, that's going to be an oxidizer. This is going to be either an oxidizer or a reducer. And a reducer is, probably a better reducer than it is an oxidizer. And so acetic acid is a reducing agent. Now, how strong of a reducing agent is it? And this is, we just take a guess. It's not the easiest stuff to burn if you have an acetic acid. Let's say you ran out of firewood, you could try burning your acetic acid vinegar. It'll burn, but it's probably going to smoke a lot. So it's probably, an okay reducer somewhere in this chart somewhere. All right, so that's redox. It's not on the chart. If it's on the chart, we could place it more appropriately. But, it could form a lot of different products. It's tougher to deal with. Okay, let's do one last example before we move on. Let's do CO2, carbon dioxide. What are the chemical properties of carbon dioxide? So first, metathesis. What are the metathesis properties for CO2? You have it? what are metathesis reactions? Metathesis reactions are also known as metathesis reactions involve what kind of species? They're favorable ion combination. Is CO2 an ion? No, so we say no metathesis reactions because metathesis reactions involve ions. CO2 is not an ion. However, this is a little bit tricky, and I'll tell you why in a moment, because of this. Acid-base. Did you know CO2 is a we saw it on the chart here. CO2 is a acid. It's a moderate acid. CO2 and water. You know, CO2 and water come from what? They come from, what's this? H2CO3 is called carbonic acid. And so carbonic acid decomposes into CO2 and water. But a tiny bit of CO2 and water can combine to form a little bit of carbonic acid. There's always a little bit of residual carbonic acid left. And so when we rank CO2, it's ranked with carbonic acid in the ranking. And so it's an okay acid, carbonic acid. This is why do you know what the pH of our deionized water is? You know what water's pH should be?
7.
Yeah. Water's pH should be neutral, which is 7. But do you know what our pH is?
6.
5. 5.5. 4.5 to 5.5. That's the pH of our pure water here. It's not pure. Do you know why it's not pure? Because it's contaminated. Do you know what is contaminated with it? It's contaminated with CO2 and air. The only way we can get rid of it and get our pH back to 7 is just remove the air. But is that so easy to remove the air? No. Those are the same thing. Well, anyway, as we get to this carbonic acid, now this is what makes it metathesis tricky, because CO2 in itself, that's not an ion, so there's no metathesis reaction, but there's an acid-base reaction that occurs. And the acid-base reaction that occurs is a little bit of CO2 might combine with a little bit of water to form a little bit of carbonic. Carbonic acid is not stable. It decomposes, but a tiny bit can form residual. And this tiny residual bit of carbonic acid can participate in metathesis reactions. And that is carbonates. Carbonates like to precipitate out with everything except group 1 and ammonium. And so it'll react with most ions. And so there is potential for metathesis based on this acid-base reaction occurring to form a little bit of carbonic acid. But nonetheless, CO2 will react with bases stronger than bicarbonate down here. That is, the carbonic acid will react with bases stronger than it's acid-base. It's an acid. So a little bit of metathesis might occur with carbonate. Then we go to redox. CO2 is on the acid-base chart, but do you see CO2 on the redox chart?
No, I've read through the chart many times. I've never seen CO2 on there. So does that mean CO2 is not reactive? Well, not everything's on the chart. So if you were to guess, what would you guess CO2 to be? An oxidizer, reducer, or both? And how could we tell? What we would do is we would look at the oxidation states. So oxygen is -2, carbon is +4, which means it's at +4. It cannot be a reducer. The only thing that this could be is a oxidizer. Is CO2 a powerful oxidizer, would you say? No, it's not a powerful oxidizer. In fact, it's kind of a weak oxidizer. CO2 is a weak oxidizer. It can only, well, then if CO2 is a weak oxidizer, what can it react with? Well, it can only react with the powerful reducers. Now, what are the powerful reducers? Tell me, if you were to sum up the powerful reducers in one word, what would you call it? The powerful reducers are? Well, there's solids that are weak reducers, too. I wouldn't classify them as solids. The powerful reducers are all metals. So, yeah, CO2 is not that great of an oxidizer. And so you need a pretty powerful reducer to react with CO2, and a pretty powerful reducer is our metal. So CO2 is used in fire extinguishers, except for what kind of fire? Metal fires. Never use CO2 on a metal fire, otherwise you're asking for big trouble, because CO2 will support combustion of metal. You don't need oxygen to burn things. We could burn things in CO2. Do you want to see something burning in CO2, pure CO2? No oxygen present. You want to see what burns in pure CO2? I'll show you what burns in pure CO2. Right here. Where did I fit here? A metal like magnesium. Let me just look that up here.
I don't know what caused that fire.
We covered it. Talk tomorrow. We know it.
I had a great one. Yeah, what did I do with that? It's here. All right, so it's easy to generate CO2. Come on. We can generate CO2 by just taking some limestone or calcium carbonate and adding acid to it. And all this effervescence is just CO2 gas bubbling. There's so much CO2 gas bubbling, it's pushing the air out of this. So it's just CO2. That's a match there. And so let's see what CO2 does to a match. So CO2 extinguished the match. Is CO2 a strong enough oxidizer to oxidize wood? No, it's too weak of an oxidizer to oxidize wood. So therefore, CO2 is used to purge the air. It purges the air, gets rid of the oxygen. If there's no oxygen, the match is not going to burn. However, CO2 is an oxidizer, so if we put in some a powerful reducer like magnesium, then that's a different story. So here's some magnesium. And so that's just magnesium burning in pure CO2. There's no oxygen present there.
The tank over here is filled with
There's lots of All right, so those are examples of just chemical properties, chemical reactions. What we're going to do is we're going to start the next chapter. We're kind of behind. A little bit of catch up. The next chapter deals with something called stoichiometry. Stoichiometry is the quantity relationships. So it's quantity relationships, i.e. stoichiometry in chemical reactions. Stoichiometry is like how much. Like, for example, if you're going to add antioxidants to wine, how much antioxidants should you add? You don't want to add too much. You know, people will complain. But you don't want to add too little. You want to add just the right amount. So how can you predict what just the right amount is? Well, we can predict that using quantity relationships in chemical reactions or stoichiometry. So we're going to spend some time talking about stoichiometry. You know, how much should you use? Well, the sulfite thing, the antioxidant, is just kind of estimated there, depending on how well sealed things are. But how much we should use is usually based on a balanced chemical equation. And so stoichiometry always starts off with a balanced chemical equation. Here's a redox reaction here. This is 4 ammonias plus an oxygen yields NO plus water. So this is burning ammonia. Does ammonia burn? Don't burn ammonia. You shouldn't burn ammonia because ammonia does burn. Ammonia will burn to form oxides of nitrogen. Oxides of nitrogen are toxic. So you don't want to burn ammonia, otherwise you're going to be breathing in this stuff. It's just small. But it'll burn. Ammonia is electron rich. But anyway, we go to this. You know, this doesn't form CO2. This is going to form NO or NO2 with water. We go to this, and how much oxygen do we need to completely combust it? Although this is not complete. How much do we need to combust this? Well, to get NO, we need, for every 4 ammonias, we need 5 O2s. For every 4 moles of ammonia molecules, we need 5 moles of O2 molecules. So we get these mole ratios here. These mole ratios can relate any of the items here. So how much NO is produced, we can calculate that. How much H2O is produced, we can calculate that as well. And so these are called the mole ratios. Mole ratios come from the balanced chemical equation for the formula. We use these mole ratios as conversion factors in chemical equations. So if 3.20 moles of ammonia react according to the equation, how many moles of H2O will be produced? And so we know the ratio between ammonia and H2O based on the balanced chemical equation. There are 6 moles of H2O produced for every 4 moles of ammonia that react. We only have 3.20 moles of ammonia. And so this is dimensional analysis, 3.20 moles of ammonia. And then we're going to cancel out moles of ammonia. We can cancel out moles of ammonia using the conversion factor here, 4 moles of ammonia for 6 moles of H2O. So the moles of ammonia cancel, that leaves us with moles of H2O. That comes out to 4.8. Sig figs are wrong here because these mole ratios are going to be infinite sig figs. This is 3 sig figs, so we should be left with 30 sig figs there. I'll add it. It's going to come out to 4.800 moles of H2O. And so when 3.2 moles of ammonia burn, 4.8 moles of water is formed. This is your basic stoichiometry problem. There. This is what we call the stoichiometry map. This is called a mole-mole conversion. It doesn't have to be reactant to product. Like this is a reactant to product, but it can be reactant to reactant, product to product, product to reactant. In other words, we take moles of A, whatever A is, you can make it be anything, to moles of B. We do a mole-to-mole conversion using the mole ratio. The mole ratio comes from the balanced chemical equation. So this is the heart of the stoichiometry map. So this slide, you don't have to spend much time looking at the slide. Actually, it's not very useful, that slide. So how many moles of oxygen are required to burn 2.40 moles of ethane? So would you think ethane is very flammable? Ethane very flammable? Yeah. Actually, how would we know? Well, let's take a look at the oxidation state. Hydrogen is +1. Carbon is -3. That's pretty electron rich. And methane is -4. It's as electron rich as you can get. It's pretty electron rich. So ethane should be pretty flammable. How about this one? Carbon tetrachloride. If I run out of ethane, can I burn carbon tetrachloride, another organic chemical? Are all organic chemicals flammable? Carbon tetrachloride is an organic chemical. Is it very flammable? No is right. How come? Yeah. Basically, chlorine is -1, carbon is +4. This is not going to burn. This stuff is already oxidized max. So this is non-flammable. This is why these are called chlorofluorocarbons. This is why chlorofluorocarbons were so popular as refrigerants, because they were non-flammable organics, which adds to safety factor. Now they're replacing some of the chlorofluorocarbons with flammable organics. So some refrigerants are actually flammable now. These were pretty unreactive too, because the bonds are pretty strong. So like synthetic blood was made out of chlorofluorocarbons and some other stuff. But this is going to be a good reducer. Not a very good oxidizer. It can only gain 1 electron, and no metathesis reactions and no acid-base reactions. The only thing is a reducer. It's like, well, what are the chemical properties of copper? When we look at the chemical properties of copper, is there any metathesis? No, it's not an ion, it's just metal. Is there any acid-base? No, there's no acid-base. The only thing this could be is a reducer. That's it. Well, that's close. I mean, to what this is in that sense. So this is going to be a reducer, and then what's the oxidizer when we burn it? Oxygen. In what forms? CO2 and water. And so the first thing we need is a balanced chemical equation. So let's go ahead and balance this. We need, here are 2 carbons. We need 2 carbons here, so I'm going to just double this. We have 6 hydrogens. We have 2 hydrogens here, so I'm going to triple this. So the carbons and the hydrogens are balanced. I don't want to mess with that. I just want to change the oxygen. So I got 4 oxygens here plus 3 oxygens. So altogether on the left, on the right side, I have 7 oxygens. 4 plus 3, 7 oxygens. And so to make 7 oxygens here, I'll just take 7 halves. But one thing that everyone agrees with is fractions. Nobody wants fractions in a mole ratio. Do you want 7 halves in the numerator or 7 halves in the denominator of this? No, it's a hassle. It's a hassle, so what we do is we get rid of that by doing what?
Yeah, we'll just double the whole thing. C2H6 plus 7O2s yield 4 CO2s plus 6 H2O.
And so we need to start off with the balanced chemical equations first. Since this is a combustion reaction, we can do that here. Okay, the states, we gotta put in the non-aqueous states. Ethane's a gas, O2 is a gas, CO2 is a gas, H2O is a liquid. Ethane is called a hydrocarbon. It's an organic compound containing hydrogen and carbon. That's it. All right, we're out of time, so we're gonna continue with this problem.